So I want to describe a project that I've been working on for a while, which has to do with improving the way that individuals or groups approach complex problems in general. It's a very, very broad project. Um, and I want to say that it's philosophical, but it's not philosophical in the sense that it's not really very speculative. I think this is a fairly concrete, applied view of how to think about complex problems in a more effective way. Um, the reason I said that was because this is a meta framework, which means it is a framework for putting together frameworks. And that can potentially appear to be academic, a little bit more speculative philosophy than a real applied toolkit. But the point here is to be more effective in dealing with complicated problems and complicated problems that are important. This is basically my best stab at what systems thinking is. And in more particular, natural systems thinking. I'm more interested in biology, I guess, in living systems. But I think that this kind of systems thinking applies more broadly than just in how biological systems deal with complex challenges, in the sense that it at least assumes that there is an objective, predictable nature, essential nature to the problem that you're trying to solve. And that is generally the assumption in natural science, in the study of natural systems, and it's a good term for that. And so if we are trying to figure out how, as humans, to better move through complex problems more effectively, rather than thinking about the human as a natural system, is the attitude or the view taken here. So the main assumption that I'm starting with is in two parts. It's that how you understand a problem determines what you do to solve it. Not that the way that you understand a problem influences what you do to solve it or is a part of how you solve the problem, but it actually determines what you do to solve it. So this is an assumption. This is just the way that we're organizing it here. It's that if you approached a complex problem like an investment strategy or a complex behavioral symptom in a clinical setting, in my case, then there is something you didn't understand about the problem that led you to not solve it completely. And that is certainly the case with plenty of the problems that we have. So how you understand a problem determines what you do to solve it. It's the theory or how you're thinking about the problem that determines what you'll do. And then further, that the accuracy of that understanding determines how effective your solution will be. And so if we're talking about investment strategy in the stock market, in whatever, the degree of error in your strategy as you look back and look at how successful it was and how unsuccessful it was, the degree of error is precisely, and this under this assumption, the amount that you did not understand the system that you were interacting with. And fair enough, because that's a complex system, complicated system. But anyway, these are the assumptions I'm using to guide this. So, drawing from these assumptions, as a coach for someone who is confronted with a complex problem, whether it's a clinical problem, a behavioral problem, whether it's an autoimmune problem, a chronic problem of some kind, whether it's just how to run a business, or this kind of thing, then the goal of a coach is simply to assist in improving the understanding of the problem, particularly as problems become more complex. For example, if you have a broken leg, it's pretty straightforward what to do. It's at least more straightforward what to do to solve that problem than it is to deal with an autoimmune disorder or with cancer or something like that. Much more complex problem, so complex that we don't even have the right theoretical conceptualization for it yet, obviously, or we would have solved it in a predictable manner. So it's about improving the understanding of the problem. This is the central idea. And then the guidelines that I'm going to present for systems models are going to be the characteristics of a more sophisticated understanding. And I'll get to that in a second. So before I do, I'm going to just give this simple case example that I'll refer back to when I go through these 9 characteristics for systems models. It was my first year of clinical training, and I was in a medical clinic in Northern California, and I was the behavioral health person there, who would just drop in on cases and see if there was anything I could do. It was fairly loose, really. I didn't even have to intervene or take part in the cases if I didn't want to, or feel the need to. Anyway, so a mother comes in bringing her 11-year-old daughter, and the daughter was biting her nails until they bled. And of course, the medical staff have an understanding of that problem that is limited by the physiological structure involved. So they know about the cardiovascular system, they know about the bones, they know about the tissue involved, they know how to stop the bleeding, they know how to treat the pain, all these structural interventions. But they don't have a cure for it because it's a functional problem. It's a behavioral problem. So structure is what the body is, and function is what the body does. These are basic principles in biology. And so I thought, well, I was right there, and I thought, well, why don't hey, mother, what do you say I just interview you and get some broad context for this problem, which is pretty much, even today, all I really do clinically, I think. And I sat down and I had a couple of guiding principles that eventually grew into the 9 principles I'm going to present in the next slide. But they were just, try to track it over time, try to understand the relationship context of the symptom, because relationships and anxiety correlate, or rather are 2 factors that are related, and just kind of see where it goes, and see what happens. And so I interviewed her for about 20 minutes, only 20 minutes. And this is the main point, her understanding of the problem changed over the course of that 20 minutes. So the initial model that she had was, it's been happening for 3 years, it's never changed, fix it. That was her model of this problem with the nail biting. Was her understanding. And so I asked questions. I said, well, so, are there any times when it's more intense than other times? What's anything big happen with you guys over the last few years, all this kind of stuff. And what she discovered, just in this broad interview, was that was about context, was that it really got bad about a year before, when she fled the state, another state, to get away from her abusive boyfriend, and the daughter was really attached to his parents. So there's the anxiety of the actual issue with the abusive boyfriend, but then there's also the attachment system that's disrupted in the relationship network. And so I don't know any more details than that. The point is that she reprioritized the effort going into that symptom based on a new understanding of the problem. She realized that this could be a result of the increased anxiety that was happening after this relationship event. And so she sorry, my screen turned off there for a second. So she she decided to come in and just keep doing this sort of contextual, what I call a systems assessment. And the symptoms went away after another session. And she was just focusing on getting the tension down and getting calm and her own functioning as opposed to the daughter's functioning. So the point was that her model changed from it's been happening for 3 years, it never changes, there's nothing I can do, please fix it, to having multiple factors that interact over time. Some of them are in the relationship system, some of them are in her own functioning, and this kind of thing. And she ended up with a more sophisticated model. And I didn't fix the problem. That's the key. So what is changing if a coach is not fixing the problem for you? And how is it that a systems assessment is so powerful? So what is a systems assessment? So what I have here are 9 principles, and this is a working list. I had 7 about a year ago. I split one of them into 2 parts, but I think that's relatively stable. These are characteristics from my own observations and review of some relevant literature. These are characteristics of systems models. A systems model being one, well, that adheres to these characteristics, but there's a lot of literature out there about what systems thinking is and this systems philosophy, and there's all these different names for people that seem to end up in coaching roles, and in some science roles, research roles as well. But there's a the terms used, particularly the term system, is used in a variety of different ways in that literature. And so I am attempting to very, very precisely define what characteristics of a systems model are, meaning none of these characteristics can be left out. So that's a more difficult task than just defining a bit of a philosophy to sort of vaguely guide the coaching process or research process or whatever it is that you're doing. Most of this comes from the Bowen theory literature, and they were principles that I inferred from that literature that was describing how the Bowen theory, which is a system theory that of human behavior, that's meant to be the kind of integrative theory that the emerging field of systems biology would ideally produce. And I think that a person who is interested in systems biology would probably agree with these principles. At least that's my assumption. So I'm grounding this in a more of a scientific approach rather than something more like a philosophy. Okay, so I'm just going to go through these one at a time. Again, these are characteristics of the way a person understands a complex problem. So if you're a coach and you're coaching someone else to more effectively move through a complicated problem, a difficult problem, an important problem, then the way that they define the problem would evolve along these dimensions. It would increase along each one of these dimensions, let's say. And one more thing, the assumption here, the proposition is that as anxiety about the problem increases, the model that the person acts out, not necessarily the model that they would write out, but the model that they act out, their actions in relation to the problem regress along these dimensions. So the more intense the problem becomes, the harder it is to think along these dimensions. All right, so that's enough. So what are they? The first one is that calling it you account for all recorded observations. And this is written in a little bit of a research mentality because I think that's probably technically the correct way to approach these guidelines. But if you're trying to understand a phenomenon, a complex problem, then the model that you develop of the problem, the way you define the problem, has to be in line with everything that's observed about the problem. And it's easy enough, if you see, for example, two people at each other's throats, they're acting out a model that's incomplete usually. Usually, all things being equal. It's like each of them are trying to contribute or get the other person to hear a vital part of the problem that they have, that they confront together. But each one of them acts out an oversimplified model of the problem that is basically just representative of their subjective view from their angle. Another interesting, let's see, I had a really good example for this in research models. It's not coming to mind right now, but there's something about this. It's that there's something that happens when you're developing a research model of something complicated, like the weather, for example. Oh yeah, that's what it was. One observation can completely throw your model out. So for example, if you have a weather model that predicts the changing of the seasons, broadly speaking, let's say that you had 1 year where there was no winter in Alaska. Alaska's far enough north to where there's always at least a shift downward. And so the model that you have, one of the core assumptions is that there is a predictable shift in temperatures or phasic modulation of temperatures throughout the calendar year. And if one of those shifts never occurs, your model is obviously wrong. And so you have to rethink the model. Now, that's a kind of a dumb example, but it illustrates the principle. Okay, so the next one is accounting for facts alone. And this is actually a little bit more subtle. It's basically the antithesis of statistics. So there is a problem with statistical thinking that is not common knowledge, I think. No, I'm not going to give that away. I want to give the more subtle description first. Let's see. So the function of statistics is to measure the degree to which the factual observations, just the observations that are made, match a preconception about that system that's being observed. A statistical relationship is a preconception, okay? And the preconceptions may be more or less accurate. A correlation of 1 is not a preconception. That's a fact. That's a causal relationship. But those are rare in natural systems. So basically what this is saying is to simply account for the facts that are presented and to keep the concepts in your model, the descriptions that you're using, as simple but broad as possible to only describe what's seen. One example of that is back from Bowen's research, and I have another slide for that. It was so Murray Bowen was a psychiatrist who was researching at NIMH in the 50s, and he housed entire families on the ward, which is the only time that this has ever occurred, so that he could basically watch them in naturalistic observation. And that's where the Bowen theory, which is a system theory of human behavior, came from. And so there is this particular vignette where there was a mother and daughter on the ward, and the daughter was intensely psychotic, meaning she was hallucinating and delusions or something, I imagine. They observed that if the mother's functioning would drop, let's say if she ended up in the hospital or something like that, or if she needed a lot of care, there are other ways to describe that, but that's the most obvious example, that the daughter's psychosis would disappear because the daughter would get into a helping position. And so long as the daughter was in a helping position, then her symptoms would actually at least go down well enough to where they weren't a problem. And so that's a very interesting thing. This project was about understanding what schizophrenia is instead of just trying to treat it. So this is more of a research context. So they're observing that. And then a second observation is that when the mother didn't need the help anymore, the symptoms would come back in the daughter. So you can theorize all you want about how that is so, but nevertheless, the observations occurred. And the staff could actually predict the onset of the symptoms in the daughter based on how well the mother was doing. So saying that a decrease in functioning of one of them, or rather, a shift in functioning of one of them leads to a predictable shift in functioning in the other, is simply accounting for the facts. It's not drawing a statistical relationship. It's saying that when this happens, this is bound to happen. And then you get into, well, maybe the next level would be to say when a positive shift in one occurs, then a negative shift in the other. It's a little bit more granularity. And then you may actually assign numerical values to that. But that wasn't what it was occurring, because to go beyond simply describing what was observed would be to impose a presupposition or a preconception, and then you start getting into statistical thinking. So, accounting for facts alone, staying away from statistical thinking if possible. The next one is fairly straightforward, but almost the most central. And that's that the model itself should describe a process. It should not simply describe the content of processes. Now, this is a big one, because it seems to be, particularly when people get bogged down or anxious or whatever word you want to use with a problem, the ability to separate content and process seems to go away or decrease. For example, you would get caught up, if there was, just back to the spousal example, if you get caught up in the right answer or what is being said as opposed to how it's being said, then typically the only way that problem is going to resolve is if you get lucky. But if you can see that that when one person raises their voice, the other person raises their voice as much and maybe a little more, and then the other person does the same thing, and then the other person does the same thing, and next thing it's a shouting match, and then if you also can observe that when one lowers their voice and thinks for themselves and starts to calm down, then the other person does the same. And you start to see that there is that reciprocal relationship, like in Bowen's example, just a much less intense version. Then you're starting to describe a process. What I just did was describe a process. And I didn't say anything about content. I didn't say what they were arguing about. I just described how they were arguing. So the ability to do that is important. And what this does is it guards against creating models that have static categorical descriptors of the problem. So an example for that, again, into psychiatry, psychology, is the DSM, which the Diagnostic and Statistical Manual of Mental Disorders. And so that contains all the diagnoses that everyone knows so well or is familiar with. The problem with that system is that it's a static categorical model. All it does is divide observations into categories. It doesn't account for those observations. It doesn't actually even say what those diagnoses are. Meaning, it doesn't tell you what schizophrenia is. It doesn't tell you what narcissistic personality disorder actually is. Where does it come from? How does it develop? That sort of thing. So it doesn't change our understanding of the problem itself. It just describes the problem and places it in a category. That's what diagnoses are. They're categories of behavior. So describing it would take a completely different kind of model to actually describe how they develop over time and how they change over time and how they interact with each other, if in fact they are separate from each other, which still has not really been settled. Let's see, a really simple example, non-behavioral example would be of the weather. So if you just say rain, it's rain. But and then it changes and you say it's snow. That's snow. And then it changes again and you say that's water vapor or that's steam or fog or something like that. And that's it. Then you're missing the process through which the water changes into the various states. And so if you have what you need for that is a common concept and a way to describe the relationship between the states, how they change over time, and how they change in response to contextual factors. And so the model has to describe a process, because when you have a static categorical model, then the only way that you can think about changing the problem is by simply knocking out what's good and what's bad among the categories and knocking out what's bad in the categories and replacing them with good categories. So if you have a disorder, that's bad, and you just try to get rid of it and correct it without understanding what it is and how it works. So describe processes, not simply the content of the processes. That could be, Michael Kerr uses this as his simplest definition for a systems model, or thinking systems rather, is thinking process. And that's a pretty powerful principle. The next one is simple on one hand, complex on another. It's that the model should account for concurrent reciprocation. This is a term that I came up with to describe effectively what is chaotic behavior in complex systems. And so I've got a little bit of a visual for that. Concurrent reciprocation is simply the assumption that there are many factors in this complex problem and that they interact through feedback loops. So a classical physics problem, like the billiard ball table, let's say, you hit one ball and it hits another ball. It's a causal relationship. There is a feedback loop in a sense, but you can actually model this problem fairly simply with a simple serial cause and effect. This leads to that, leads to that, leads to that type of model in a computer. Another example is if you're going to model a gravitational field of two planets, you can actually do that in a step-by-step manner. A affects B, B affects A affects B, and each one of those is just a little bit of effect so that it goes around in a circle. Now, you can't use that type of thinking when you have another planet, because now you have three feedback loops. Each gravitational field affects the other, and as soon as A has affected B a little bit, C has affected B and B and A have both affected C. So they're all mutually influencing. This is a completely different kind of a problem, and you can't model it in a simple serial model. It doesn't work. You have to actually change the way you're thinking about things. And so in human systems, of course, in instinctual systems, if you're talking about the way that people have basically reflexive automatic reactions to each other as a process, regardless of what they're talking about, but their level of arousal affects the degree to which their model of a problem regresses and progresses along these dimensions of sophistication. And the influence that's occurring between people occurs in these feedback loops simultaneously. And so they're running, and this occurs even when when all the people aren't in the room all the time, I should add. So anyway, so the feedback loops are running. That's the reciprocal part. It's reciprocal influence from one factor to another factor, and that all of these reciprocal feedback loops are running concurrently, meaning at the same time. So this is concurrent reciprocation. So this gets you out of a simple cause and effect, linear causal type of a model into a much, much more complicated way of thinking. Sophisticated, I should say. All right, so the next one is describe a change in one variable as change in another variable. Could seem self-evident, but this keeps you from isolating the factors in the model. All right, so, and it makes it so that whenever you describe a change in one variable, it's always described in terms of change in another variable. So instead of just going out and tracking the temperature, you're tracking the temperature in relation to the air pressure, in relation to the precipitation, in relation to the sunlight, with cloud cover and all this kind of stuff. So it's always like when the temperature increases, the cloud cover also increases, and that's holding the hot air in. Or in other climates, when the temperature increases, the cloud cover decreases because direct sunlight is a bigger variable. It's always describing them together. And the next one, and so I've got an example for that one, but it's tied together with the next one. So the next one is describe an equilibrium. And so I'm going to describe number 5 and number 6 using this model here that I put together. So this is a simple software program. It doesn't really do anything other than just take these variables here, let's say it's a bar graph, and it just adds up the degree above 0 and below 0. So it's just a floating point number, and it adds them all up to a total. That's all it does. And so if these are the factors in our model, like I was just saying, let's say one of them is ambient temperature, another one is air pressure, and another one is cloud cover, whatever. Or they could be the functioning level of 5 people in a family or something like that, in order to understand the relationship between them. This is coming from Kerr's article, A Systems Model for Disease, which is basically saying that a systems model describes how equilibrium is maintained among the factors in that system, or components in that system, or whatever it is. And the assumption is that when one variable goes up, another variable goes down. So it's a zero-sum game in that sense. It's that, let's reset. For example, if we've got a small company with 5 people, obviously it's possible for one person to take on more responsibility than another person. And so the assumption here is that, and I'm not making this claim necessarily, it's just an analogy. Let's just say that when one person takes up more responsibility, so long as they all have the same holistic, the goal together, agreed upon goal, then the other person doesn't have to take on a little bit less, quite as much responsibility. However, if these two are set at those responsibility levels, let's say the other ones are also changing. So the question is, once I've made that change with the first 4, then where is it that this last one has to fall to bring it back to 0? The amount of calories, let's say, that are burned towards the common goal. Well, they've got to come way down here. So all this is pointing out is that a systems model is describing an equilibrated system. And human groups as instinctual systems, you could say emotional, but that word has too many different meanings. So there are predictable patterns in the way that people interact that are shared among many species, more or less, and that the functioning level of one person is related to the functioning level of other people, particularly when they're related. So that's just to say that, coming back here, number 6 is describing a systems model describes equilibrium, assumes that these are related through concurrently reciprocal feedback loop, and that when one goes up, another must come down. And the question is, this is the key question: what is the model that accurately describes how the load is distributed among all of these factors? And that is a very, very nuanced and subtle question. I actually wanted to turn this into an example that functioned on its own, where I would put the first one up and then the other ones would automatically adjust to find an equilibrium. And while I could do it, I started to program it and thought, oh man, this is really actually a very sophisticated question. It's just like the other slide that I had going back here to the 3 planets instead of the 2. There is a qualitative shift between 2 factors and 3 factors. And so trying to make a model that functioned on its own with just the first 3 is a very complicated problem, actually, even if you're not trying to represent a natural system like a human group. So a systems model describes equilibrium. A change in one variable is always described in terms of a change in one or more other variables. If you're just tracking a variable on its own, then you're losing the scope of the system. So on to number 7. That each variable should have a clearly defined relationship to every other variable in the system. You could replace variable with factor, but that the model of the problem is only changed when the change accurately, or not accurately, clearly just has a relationship or accounts for every aspect of the system. So the whole thing works as a coherent whole. And I think that, well, let me give an example first before I give that other example. So the back to the weather model, or the model with rain, snow, etc. So you might have an expert on snow, and you might have an expert on rain, and you might have an expert on rivers, you might have an expert on oceans, and another one on humidity, etc. You can keep going on and on and on. But if you don't have a process, if you don't have knowledge of a process in place that explains how all of those observations, factual observations, are related, if you don't have a way to explain how the ocean affects the water vapor, which affects the clouds, which affects the rain, which affects the rivers, and in a cycle, then you can't. Then you're going to have much less predictive power, and you're not going to be able to deal with problems that are related to those phenomena, like predicting the weather, or like understanding your impact on the environment that you're in, that kind of thing. And so what you need for that is if you've got these disparate models, if you have these isolated models with each one with their own expert, and you want to actually get all those people to, all those experts to pool their expertise into a much more sophisticated way of dealing with whatever problem this knowledge is helpful for, then you need a central concept to organize everything that they're doing and that they know. And that central concept would be water and the various states that it moves in, and then understanding how it moves from one state to another and how that's related to temperature and that sort of thing. So the question would be to take this model and say we have these various states of water, and we've got a central concept to organize how they all fit together, and to ask, can you describe how this part relates to this part? How does it that state relates to that state? How is it that the rain is related to the ocean? It's like, well, okay, the water, the temperature rises enough and it evaporates into the air, it turns into clouds, and then it falls enough and then it turns into rain, and that's great. And then maybe if it falls a lot at the right time, then it turns into snow, and so on and so on. So the question would be, how does each variable relate to every other variable? In conceptual systems, like a scientific theory, for example, Bowen theory has 8 concepts in it. The question is, how do you know when you can add a new concept? Well, I think one of the answers to that is that You can't add a new concept to the theory until it has a precisely defined relationship to each other concept in the theory. So all the concepts are interlocking. And without going into details about Bowen theory, what this does is it just keeps the model from becoming fragmented, which is the case with some of the early psychological models. For example, Freud's model was kind of fragmented because he had these different parts that didn't quite have a well-defined unity to them. So basically, your model of the problem's got to be coherent, it's internally consistent, rather. Okay, so the last two are a little simpler. Number 8 is generating falsifiable predictions. Now, this is just anchoring the model in the objective domain. It's saying, well, okay, so you've got this understanding of the problem. How well can you predict how this problem will play out if you do A, or if you do B, or if you do C? How well has it played out? How well can you predict the past data, too, based on what you know of the system? So this is just Karl Popper's criterion for science, which is that you have to be able to construct a scientific experiment that can have a false outcome or a negative result. You have to be able to have a hypothesis that can be wrong. And it seems like these are hard to spot in practice. It turns out, actually, that his critique was about Freud's theory of human behavior, which Freud and Adler, and he said that both of them had produced, I think he was speaking about Freud in particular. Well, anyway, he referenced both of them. He said, while they had produced very impressive, sophisticated theories of human behavior, and he has no doubt that what they're seeing has validity and importance, all that they had proven was that they could explain anything, not that their explanations were correct. And to know that they're correct, you have to make a blind prediction, which is a hypothesis that can be wrong, but turns out to be correct. So, for example, if you said that, if you said something like, well, if you integrate the self, then you'll stop having dreams about your mother. Well, great. And this is kind of a Freudian thing. So it's an interesting thing, but it's linking a symptom to a relationship, which is a very big deal. But there's no way that you can, it's like, how do you know if you've integrated the self? What does that even mean? How do you know when you haven't done it? So the problem is that you can always just say that, well, as long as the symptom doesn't go away, then you must not have integrated the self. That's not a prediction. That's not a blind prediction. It's not a falsifiable prediction. So anchoring an objective reality. We're assuming, because this is a natural systems model, we're assuming that there is a right and wrong way to understand the model and how effective you move through that problem. Rather, there is a right and wrong way to understand the nature of the problem that you're up against and the degree of error that your actions reveal in your understanding of the problem is how much you don't understand about the problem. That's a strange sentence, but I think you understand what I mean. So generate falsifiable predictions. So the last one is more one of mine. This is just basic science, particularly in biology. Using terms that don't depend on the human species. Now, I have to explain this. So it's basically trying to use objective terms instead of subjective terms. There's a bit of overlap with number 8 with that one. I used the example that I used about, integrated the self, like in Freud's theory. Well, no one knows what that means, really, in objective terms anyway. And so the question would be, and this is the little heuristic that I put together. If you're developing concepts to understand a problem, does it, and I guess this applies more to living systems. I'm not sure about that yet, but do the terms that you're using to understand the problem equally and accurately describe the behavior of a person, an ant, a plant, and an electron? Now, the first three at least fall within the realm of biology. But to say, for example, that a person is anxious may or may not apply to an ant. You might just equate anxiety to arousal or something, and you say, like, when you bang your foot on the ground next to the ant hill, then all the ants kind of start, they all activate and start running around a lot faster, and then eventually they come back down again to a normal level of arousal. And you could say, okay, so they're anxious. I don't know if that's accurate, but you could say that. But does that apply to a plant? What if there is some equivalent to hyperarousal in a plant? Maybe it's a metabolic process that speeds up or something like that. Does that accurately describe that? And by accurately, I mean, is it useful? Does it actually help you solve problems related to that phenomenon, to that plant? And then when you take this to the ultimate level, it's to the physical level, which is, does it also apply to an electron? Just, being a subatomic particle. Let's just say we can't go beyond that conceptually. At least I can't. So it's the lowest level. And basically it implies something like an organismic theory, meaning a theory that defines what life is, which we do not have, by the way, that reconciles how basic physical and chemical laws give rise to what we call biological phenomena. We don't really know how that works. We have some hypotheticals, but there isn't an accepted theory for that kind of thing. But, there are still universals to relationship systems. And so you could say some of these guidelines that I'm throwing out here hint at ways to describe the behavior of systems at all four levels of analysis. For example, are you understanding the system as an equilibrated system? And does a change in one part result in a change in another part? Is an atom an equilibrated system? Is a strand of DNA an equilibrated system? Does it have a process that you can describe that captures the behavior of that system? Is it possible to account for facts alone or draw statistical relationships? So there are these ways that you can put together models, a more sophisticated way of understanding even a non-living system. And that's why I'm calling this models of guidelines for models of natural systems models. Because it doesn't necessarily adhere just to living systems, just to human systems, but that developing a more sophisticated, more scientific way of understanding a complex problem in general has some predictable characteristics. And I think that these are at least a good starting point for what those are. So how does this work in coaching? How does this work in personal life? Step 1, define the problem. How do you understand how this problem works? And then just take that understanding, which is a model, and just run through the guidelines. And use the guidelines to ask new questions about the phenomenon itself, about the problem, to try to become more knowledgeable about the problem, to understand how it changes over time, to increase the number of factors that are considered in the model, to make it more sophisticated in that sense, to make an understanding of the relationships between how those factors change over time, to be more accurate, to keep it as objective as possible, not to ignore a single observation that refutes the model. And so instead of changing the observations by ignoring some observations, you change the model, this kind of thing. Make sure it describes a process, and on and on and on. So as a coach, I'm thinking, in order to help someone else through complicated problem that they are responsible for, that would mean that I'm not fixing the problem for them. Instead, I'm just sort of like a research committee member who is helping them think about their methodology, which is a separation between process and content in itself. It's not what do they do about the problem and is it a good or a bad idea. It's how are they thinking about the problem? How sophisticated is their understanding of the problem, and can their understanding of the problem improve along any of these dimensions? So that's it. It's just to ask questions and more questions about about how they understand the problem, and then let them make up their own minds about what to do about it. That, I think, should, and so far in my experience does, create a thread of pertinence between the factors in the problem. What do I mean by that? I mean, if you start out, for example, with a medical problem, a physiological problem, that is a difficult problem. And like I was talking to someone about joint pain recently, and I was just curious about how they were thinking about that problem because it had been such a big deal for such a long time. And I asked any question. I asked any question about context. I was trying to keep as many preconceptions out of it as I could, and ask how and get a better understanding of as many factors as possible that seemed pertinent. That's the thread of pertinence to the problem, as reported by the person that I was interviewing about this joint pain issue, and to track how those factors change over time and relate to each other. And to assume that she's an equilibrated system and that she's part of other equilibrated relationship systems, for example, and that changes in one area of these systems must lead to changes in another area, and just to try to change the understanding of the problem by being curious about it. And that appears to be counter to standard medical training, which is also important. I mean, not to say it's not important, because the medical training has to work in the way it works. It's generally speaking, when a physician approaches a symptom, they deduce or do some kind of a differential diagnosis to determine what exactly the problem is according to their known framework. Because when you can pinpoint the problem, then you know what to do about it. And that works when the problems are better understood. It works less when the problems are less understood. And behavioral problems are certainly in the less understood area. So anyway, that was an interesting thing. And the point was that while this more or less came from the Bowen theory literature, these guidelines, and from my thinking while relating to that literature, Bowen theory describes relationship systems. And it is rooted in systems thinking, which I am defining as these principles. But it is not the same thing as thinking systems. Some problems are structural. And in businesses, sometimes a new person has to be hired. The structure has to be changed, not just getting the current people to function in a new way. And so the point is to just think systems. Follow what I am calling the thread of pertinence, which means just learn about the important factors for the problem without any preconceptions. And if it leads to a relationship system, then it leads to a relationship system. If it doesn't, then it doesn't. There's no evidence for assuming that it is part of the relationship system. But that should make the role of the coach a bit simpler. Okay, so I think that's all I can fit into this for now. I should say also, I meant to show this, but each one of these dimensions has its antithesis. And so here's the 9 in short form listed out here. And then this is where they end up when a person's model regresses to a less sophisticated form. So the problem with not accounting for all recorded observations is you only end up with a partial view, which means you're going to have a partial solution. Not accounting for facts alone means you fall into statistical thinking, which is reductionistic. By definition, measures preconceptions. It doesn't change your understanding of the problem. It just measures, well, necessarily, it just measures the degree to which the problem matches the way you already think about it. So a statistical relationship is a preconception. The model itself would define a process, and as opposed to simply the content of the process. So for example, how people are relating as opposed to just what they're saying. So how they relate regardless of what they're saying. And when that occurs, when the model regresses along these lines, it becomes more a model of static categories that don't change over time. They're just static categories. The model would account for concurrent reciprocation, which assumes reciprocal feedback loops operating at the same time. And the regressed version of that at the bottom end of the scale is cause and effect thinking, meaning that it's another kind of a partial view where you think that just one thing causes another thing as opposed to it being the result of a mutually influential confluence of many factors, and that confluence itself actually changes over time. A variable is change in another variable, and what that does is it keeps the model from getting fragmented from you just describing one variable all by itself. It keeps the whole thing in view, the whole system in view. A systems model describes equilibrium. Again, in human systems, it keeps you from thinking in an individual sense and always holds that individual in the broader context. In biology, that's called isolationist thinking. It's sort of similar to this number 5, but I'm still working on that one. You have to be able to describe the relationship between all variables in the system. It has to be a system that's a model that's coherent in itself, to itself. All the parts have to relate in a defined way. The opposite of that is having disparate models, having models that are separate. And separate models means that you end up with separate solutions, which means that they may be out of line. A fix for one problem may be out of line with a fix for another problem. That's also similar to a partial view. You also want to make falsifiable predictions. That keeps your subjectivity out of it. It's like prove yourself wrong. I love the Feynman quote, science is the act of bending over to prove yourself wrong. Okay, so falsifiable predictions. How would you predict this plays out? And is your prediction an objective one? Or is it one that will always be correct? And the last one is generalizable terms, another way of saying terms that don't depend on the human species for their interpretation. The subjective terms, the feeling terms, the emotion terms fall under the category of being anthropocentric, and I think that one way of understanding how this dimension regresses is that it's an overemphasis on culture in human systems, at least, and an underemphasis on biology. So those are out of balance. And usually people say that, human culture, since we came online and started recording our history, it's like everything since then has had the biggest impact on our behavior, and I beg to differ. But anyway, it's just keeping from anthropomorphizing the terms. So I'll leave it at that. And if you ever have a chance to get a hold of me, I would love to hear what you think about it. Thank you.